Hello guys, how are you doing? So today we are meeting for the first introductory lecture in structural analysis. Okay, what are we talking today about? We are going to be talking about what is analysis and design process, the type of structure, of course the introduction of structural analysis, and then at the end we're going to be discussing a little bit about specification and building codes. That's the material that I have for this lecture. First, this is copied directly from your catalog here at the university. For this class, structural analysis, we're going to be dealing with topics in structural mechanics, analysis of determinate and indeterminate structures by flexibility and stiffness methods. We're going to have computers and laboratory exercises and experiments on behavior of structures and materials. This is it. So basically, the whole program, the whole class is going to be divided in several topics which are not exactly these corresponding to the modules, but they are closely related to classification of a structural system and types, idealization of a structural system and loads, review of statically indeterminate analysis and equilibrium for shear moment diagrams. So you have to go, guys, from now, not from now, you should have done it from the beginning. Before taking this class, you should have been, keeping that material fresh in your mind, updated. But go back and review shear moment diagrams for structural determinate materials, statically determinate beams, and also for trusses. We're going to do more statically determinate analysis in trusses, cables, beams, and frames. Specifically, I'm going to touch cables and frames, and cables is something that you already covered. We're just going to add a little bit of extra, but this was covered in statics when we discussed particle equilibrium. This is extremely important. This is one of the takeovers from this class, the main points. Influence lines, deflections. This part, when you use double integral method, you use that in hopefully you learn that in mechanics of materials, so we're gonna, or solid mechanics, whatever you wanna call it, or mechanics of deformable bodies, which is another name for that class. And we're gonna just touch this, the double integral method, a little bit, but we're gonna be doing more emphasis in the consistent deformation or virtual work method and force method for that. Then we're going to use force methods for indeterminate structure, and we're going to do displacement methods for indeterminate structure. And by displacement methods, I'm saying we're going to be touching slope deflection, and we're going to be doing also a moment distribution for this class. So what is a structure? I always start my lectures like that. Big open question, what is a structure? And then I ask the students, and they start, oh, a structure is, I don't know, a building. No, yeah, a building is a structure, but this is not the definition of a structure. Or define a structure. Okay, a bridge. Yeah, a bridge is a structure, but it's not the definition for a structure. So basically, a structure is a system of connected parts in a certain way to serve an intended purpose. And I know this is a very, very broad concept, and it's true. The skeletal system, that's a structure. Also, system of connected parts in a certain way to serve an intended purpose. But in our realm, which is when we're moving, where we're dealing with buildings, bridges, etc., so structures are a system of connected parts used to support a load, and I will add within certain parameters, because that's the other part, to comply with certain requirements, not only to support the load. That's basically what we are using as a structure. Now, another thing that is really important, and I have done this discussion with my students, even though PhD students, what is analysis and what is design? There is a difference between analysis and design, and I'm pretty sure that if I start right now and I ask you a question, define analysis and define design, we're gonna have a bunch of different type of answers, some of them partially correct and some of them really incorrect. But anyway, I want you to go and do a very, very good distinction between what is analysis and what is design. And I'm going to start defining what a structural design is. And this is a concept from Salmon, and there's a bunch of poetry here, if you will. But Salmon defined structural analysis, or structural design, I'm sorry, as a mixture of art and science, combining the knowledge and intuitive feeling to produce structures that, and this is the poetry behind the definition. Now the meat of the definition, the really meat and bone of the definition are these: to produce structures that are safe, economical, and they have to serve to the intended purpose. That's basically it. So design is an iterative process by which a solution is obtained. But look at this, an optimum solution, not only a solution. So it's an optimization process, and I'm going to repeat that: at the minimum cost, minimum construction time, which at the same time reflects into minimum cost, minimum labor, once again we are referring to this, and maximum efficiency. For what? Balancing all of these. For what purpose? To produce structures that are safe, economical, and they serve to the intended purpose. That basically is design. Now, there are different stages in the design procedure. The first one is the functional design, and the second one is the structural design. Functional design refers to what? To what this is created for. What can we do with this? How I'm going to distribute the spaces, ventilation, illumination, how the people are going to move, or the goods are going to move through these spaces. Is it going to look good? Is it going to look ugly? Is it going to be amazing? So basically this is work of architects, not engineers, because they are trained specifically to deal with these type of situations. Now the structural framework design, basically what it is selection of sizes, materials, type of elements in order for the service loads to be safely carried, the displacement within acceptable limits, and when the structure is functioning also, all the live loads or all the loads that are going to be applied to that structure, either by use, occupancy, or by environmental conditions, are satisfied. So design procedure starts, if we combine those, by planning. What is planning? Planning is this: oh, I have this lot of land and I want to do something. What can I do there? In that part of planning, once again, the architect plays the fundamental role here. So it deals with the zoning, with the ordinances, the distribution of the spaces. And after we have that, and the architect provides you with his vision of what this project is going to be like, and then it comes what is called, or I call, preliminary structural configuration. And in my opinion, once again, this is a very, 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 very tough situation, very tough job to do, and to do it correctly. It requires a lot of experience from the part of the engineer, because the architect is going to give you this, and at most is going to give you his vision, what he thinks they should do with the structural configuration. Structural configuration means, oh, the architect gave me this, and now I have to start saying, oh, I'm going to put the columns in this way. You see, these are the columns. Or the architect can give me the location of the columns as he or she thinks they should be placed in this project. Sometimes they work, sometimes it doesn't work. I'm not gonna criticize this, especially not at this level of the class, but you see there's a lot of irregularities here with the frames for these columns, because how are you gonna build this? I don't see straight lines except this part here. Now, why these columns are in this direction with the inertia, the biggest inertia in this area, in this direction, and not in this direction? That is part of the preliminary structural configuration that the engineer has to create. And you might have sometimes to fight people and say, listen, this is not possible to do it like that, or it is possible but it's going to cost you. Look at that, one column here and one column here. Why you don't have any column in this part if you have the possibility to place columns there? So that's part that between the engineer and the architect has to come in agreement. But the engineer is going to be always from the structural point of view, and the architect mainly is going to be from the static point of view. So that's what I mean preliminary structural configuration. And then the beams, the girders are going to be girders here. Are the girders going to be exposed? Are the girders going to be covered? Whenever I have, I don't know, a crossing in the doors, are those girders going to be affecting somehow the entrance, the ducts for air conditioning? I don't know. That is a really difficult part to do, but it's a very important part to do. So once you have the preliminary structural configuration, usually students, when I go to these lights, okay, lights. Usually when you go to these type of situations and you ask the students, they mention here loads, determining of the loads, the loads. But how are you going to determine the loads if you don't have any pre-dimensioning? Well, let's say, and we haven't discussed loads yet, but the type of loads that are affected only by occupancy itself, yes, you could know those loads. But the other type of loads, and I don't want to define it, those are called dead loads, but we're going to define it in the next part of this lecture. How are you going to know how much is the weight of something if you don't know the dimensions of that something? So basically what you have to do is do a preliminary member selections in which experience plays also a major role here. You get a feeling of the structure when you see it, and you might be right or you might be wrong, but it's a starting point. And once you have that preliminary member selection, then and only then you can have a kind of comprehensive understanding of what are the values of the loads or the magnitudes of the loads that are going to be acting here. Now, once you have the loads, then you perform the analysis, and that brings you to the definition of the analysis. What is analysis then? Analysis is the process by which we determine if the loads that we have in the structure are able to maintain our members within the parameters that we need to. That's it. So analysis is, if you will, you have every single value, you have the loads, and you have the dimensions, and you have everything else, and then you verify if that complies with whatever you are looking for. Versus design is you don't have the materials, or you don't have the member configurations, or you don't have the member dimensions. So you have to start iterating in order to get that. Once you do the analysis, then the question comes after the evaluation. What is the question? The question is, do all members meet the strength and serviceability criteria? And if they don't, wait a second, do you know what serviceability means? Well, you should know what serviceability means, but for now, let's keep that over there, serviceability, and I'm going to explain that after this. So if the members do not meet the strength and serviceability, what do we do? Redesign what? We have to go back, right? But I don't know where do we have to go back. We have to go back somewhere else. Either to, I don't know, it could be planning, it could be preliminary member selection, it could be structural configuration, it could be, hopefully it's going to be here to this one. But there are cases that no matter what you do, the solution is coming here, and change columns, for example, in this example. Nice, very nice. So for example, in this case, change the columns, and if you have two, maybe you need a third one to reduce the span length. I don't know. But what about going back to planning? Well, when you go back to planning, it's at the end. It happens that no matter what you do, whatever the architect told you he wants to do, his vision, is not possible to do it within reasonable amount of money or something like that. So let's say that you go back and you come here and then you ask the same question and it happens that it's yes. Well, if the answer is yes, that's it, right? We're done. Nope, that's wrong. We are not done. Because then we have to ask ourselves, let me ask you this question. Let's say that you have, and I'm going to extremely exaggerate this. Imagine that you have a 3 feet distance or 2 feet distance, like that. Make it 2 feet, 2 feet distance, this big. And then you put on top of that a steel beam, W beam or steel beam, any beam. And that beam is going to be 4 inches in base by 20 inches in height. And you put that beam over there. And then you put a load of 1 coffee on top of that beam. Is that beam going to be sufficient to support that weight on top of that? Yes, of course. But it's not optimum because it's completely and utterly over designed. So then you have to verify this part. If it's not, because it's too expensive, it's too big, too much material, it's a waste, and you don't want to do that, then you can go and you can refine by maybe finding a preliminary member selection, changing the dimensions, reducing them in some cases, augmenting them in some other cases, or maybe you can go back here also and say it in this case, you know, yeah, in this case having 2 columns separated a distance of 10 meters, it works. But what if I put an intermediate column at 5 meters, and then I have 3 columns now? The length of the span is going to be reduced, which means this beam, whatever is steel or concrete, reinforced concrete, is going to be smaller also. The moments are going to be smaller, and the dimensions are going to be smaller. This is something that it has to be taken into account. If the final decision is here and you got the optimum structure within the parameters that you wanted to do, that's it. And then what comes after this? After this, you just get an emoji of Elvis saying thank you very much, we're done, and that's it. That will be kind of a design procedure for the structural point of view. And they can present variations. This is just my representation of what design is. But whatever you do, don't forget Elvis has to be at the end. Okay, what it says here, serviceability, strength, criteria to meet the parameters. So some of the parameters that you have to create and you have to check are what? Tension and compression. You know that, right? You have to verify tension and compression. You have to be careful because the slender members in compression may buckle or will buckle probably, and if they buckle they become unstable, and the strength is sufficient but the instability over there, it might just make the structure collapse. When you have very lightweight structures, so you might have excessive vibration, and there's also specifications regarding vibration. What else? Torsion, deflection, shear. All of those are verifications that you have to do, and many more. Connections, splicing, connections of the steel elements, splicing between rebars in concrete. I don't know, just for mentioning a few. Now, when we talk about serviceability and we talk about strength, those are called kind of limit states. And the limit states are, and we're going to discuss this in the next lecture also, but basically a limit state is those values where the structure cease to fulfill the function for which was created for. So there are two basically big problems here in limit states, or big milestones. One of them is the safety, the strength of the structure. And those limit states are yielding or crushing of the sections, rupture of the section, fracture due to fatigue, cyclic load, load on load, load on load, bridges, for example, connections in bridges. Stability against buckling, we already discussed that. Overturning of the structure, sliding, sway, drift. Sometimes you have two buildings close to each other and you have earthquake, and then the buildings start moving and the drift can make them connect, shock one against the other, crash once against the other, I don't know. And those are limit states related directly with the strength. If something happens like this, be careful because the structure is in trouble. Now you have another type of limit states which is called serviceability, and it's not only deformation, it's called serviceability, and I define this more from the point of view of comfort, psychologically and physically comfort for the structure. Some of them are, for example, deflection. Is deflection an issue? Well, it depends on how much is the deflection. There are parameters for the deflection to be safe, and there are other parameters for deflection just to be there. Oh yeah, the structure is deflected, so what? But it's strong enough to keep everything that I need to? Yes. So for example, if you have a roof and that roof is deflected, just for you to have an idea about deflection, okay? There are different considerations for that to be considered within specification. If it's not plaster, and then you have the roof and then you have a ceiling covering that roof, it might be deflected, you don't see it, it's within parameters, it's there, nobody notices it, and nothing happens. Now if it's plaster, and it's the same deflection, then the plaster is going to crack. Would you like to see those cracks? Would you feel comfortable living in a place with cracks due to deflection? No. Even though if you're an engineer, you know that it's safe, but it's uncomfortable. That's what I call it, comfort related to. Another example, you have a window and you have a girder on top of the window, and that girder deflects, and because the girder deflected more than it should be, or it wasn't taken into account as it should be, now you start having problems with the window, and the window stop opening or closing, or worst case scenario, cracks. Does that mean that the structure is going to collapse? Probably not. Does that mean that it should be investigated and corrected? Definitely yes. Now vibration, I already mentioned it before. When you have a structure and it's very thin with long spans, aka for example bleachers on stadiums, or if you go to any shopping center, any mall, just stay on one of the malls, the shopping centers. Stay there, see it, especially if those are the new modern type of malls, and see what happens when people walk around, just walking around. You're gonna be in your bench, sitting there, and you're gonna feel vibration. Does that mean that that building is unsafe? No, by no means. But that type of lightweight structures induce vibration, and you should take care of that, because a lot of vibration might produce a serviceability issue. Corrosion. Is corrosion important? Yes. Wait a second, why corrosion is here? It should be here, right? Because it's a safety issue. I don't know, it might be. Is that a safety issue? You see, it's corroded. Now, is that a safety issue? I still don't know. What is the area of this? How much is this compromised? Is this hollow? Is this solid? Imagine this is solid. how much is this area, the corroded area that is not working compared with the solid area of cross-sectional area of this? 0.01%? I don't know. What about this one? What about this progression? Same situation applies, right? What about this one? Oh, well, now we are a little bit different. We have a spall in there. What should I do? Take the column completely out, demolish the column and put the new one? I don't know. What about this one? It's falling in pieces. So there are different degrees of corrosion. Most of the cases of the corrosion are gonna deal with serviceability, but they have to be fixed because then they can be a structural problem if you don't fix them. Reparable cracks, okay, because there are cracks and there are cracks. And on top of cracks and cracks, there are also cracks. What do I mean by that? Well, what type of crack is that? You have to pay attention, not only to the thickness of the crack, but the location of the cracks. Usually 45-degree cracks at the supports, that means that you have a problem with shear. What problem? I don't know, we have to study the case, but that's what happened. If you have longitudinal cracks on a girder, for example, that might have something to do with the longitudinal rebars, but it's maybe because they are corroded internally. I don't know it either. We'll have to study, but we have to pay attention. Now, if you have transverse cracks in a beam, reinforced concrete beam, what does that mean? Well, the concrete is always cracked depending on the magnitude of those cracks, but usually those cracks refers with section, bending of the section. Is the bending too much? Are the confinement being lost? I don't know, but depending on the type of cracks. So if you go and you see a wall like that and you see that crack, that probably is nothing. Now if left unattended, water can start penetrating, going into that and creating more damage. So is that gonna collapse the structure? I don't think so. What about this? Is that gonna make the structure collapse? I still don't know it, but definitely this looks more severe than this one. This might be just a retraction plaster crack, but this might be produced by a settlement in the foundation. One side settled more than the other one, and the crack in the wall is not as important as the crack in whatever structural member you have in that structure, and then you have to pay attention closely to that one. What about this type of crack in the column? Is that important? Is that reparable? Once again, you do not know, but the crack itself is not the problem. But when you investigate that, if you find that, then you go back into the corrosion problem, and here you can see that the main steel is being deformed and the confinement is being lost here, and that is an issue. So some of them will become a safety issue if left unattended. That's basically it. Type of structures, well, you name it. You can start talking about that the whole day. I'm just going to mention several groups. Frame structures. What is a frame? Connection of elements, beam columns or beam columns, forming these type of configurations. These babies here are some of the projects that I did when I was back in Venezuela. My projects, I mean, I designed, built, and sold those projects over there. In this one here, 26-story building, I just did the analysis design, the structural design of this project here. And this was in a seismic area, highly active seismic area. So you have to do earthquake design. But all of these type of structures basically are frame type of a structure. Then you have bridges. You have beam bridges, for example, girder bridges. You have another bridge here, and this is a truss bridge. Then you have domes. You see this roof here? Well, this is a dome. Then you have suspension type of a structure, bridges again. You see, this is called suspension bridge, and this is called cable stay bridge, even though both are cable bridges. Then this is a suspended roof here. You don't see it very clear, but there are some cables here suspending that roof from that mast. Then you have these skylift or funiculars. those are definitely cable structures, and we're going to be covering these type of situations also in this class. Then you have shell type of structures, and then you have arches. Look at those arches. Look at that beautiful arch. This was a beautiful arch. It doesn't exist anymore because they didn't maintain it and start collapsing, and they imploded it. And this is at the mall at Millennia. It's a 3-hinge arch, truss 3-hinge arch. You have hinge here and here and here at the ends. So those are arches. We're going to be studying that and covering that also in this class. And then you have the movable type of structures. Those are movable bridges. This is a bascule type of bridge. It's a Sunrise Skyway bridge. Sunrise Boulevard bridge, I'm sorry. This is a swing type of bridge. It just moves and rotates in one direction or in the other direction to allow the traffic to go. This is a lift type of bridge. Traffic goes in this direction. When the boats come, if it's big enough, then this stop the traffic, lift, boats passes by, come back down, and the traffic keep moving. This is another type of bascule bridge, but it's really weird, right? Look at that shape over there. This is a rolling bridge. By the way, I have an example of that somewhere. Let me see if I find it. Yes, I found it in my desk. Look, that bridge is this bridge. That bridge. This is a model of that bridge. It opens and it's a truss bridge. That was a project that one of my static students did as his final project in the class. What else? Then you have retractable structures here, retractable roofs, truss roof retractable. Here, roof. You see? That can come in this way and this way. And then you have, this is in Seattle, and then you have moving architecture like this, dynamic architecture. This is located nowhere yet. This is from Fisher. It has been planning on doing it for several years now in different parts. But the concept is that the floors can rotate independently. Now this is built, and it's also a rotating structure. It's in Brazil. It's called the Sweet Volar in Brazil. These can rotate 360 and go back to the original point again. So just another type of structures. Now what are those? Those are specifications. AISC, ASCE, ACI, American Institute of Steel Construction. This specification is, or the American Concrete Institute, for example. Manufacturing companies of steel and researchers, they produce guidelines, norms, so you can work within safety parameters according to their judgment. That's basically what they are. But you, at the end, you're gonna have always the ultimate responsibility for a safe structure. Can you go against a specification? It's not recommended, but yes, you can. Don't do it. But if you justify it and you want to do something that is not here, once again, I'm telling you, don't do it. But they even say that. They even say you can justify, and no matter what you do, at the end you're going to be responsible. When you put your signature over there and your seal, you're going to be responsible for that. Legally, I think it's 10 years or something like that. Morally, forever. Something goes wrong, it's your responsibility no matter what. Legally, I'm not so sure if it's 10 years. In Venezuela, it was 10 years at least. So don't go against the specification, but when you read them, the good thing is you're going to have always somebody with more judgment that you have, that you can learn from, and you're going to have a bunch of time to be familiar with these specifications. But there are some cases that you can we're gonna be discussing this. Once again, don't go against the specification, never ever, because theoretically, that group of people, they know way more than you do, and they have been working for way longer than you do, and they have done research about that, and they know what they are saying. But at the end, keep this in mind: the designer has the ultimate responsibility for the structure. Now, what is the difference between a specification and a building code? And you can have specifications and standards and codes and building codes, but specifically talking about specifications and building codes. Those are specifications. Once again, those are norms. Should you get out of the norms? No. Will be illegal if you go out of the norms? No. But don't do it. Now, when those specifications are adopted by the government, and they are imposed by the government, then they become law and they become building codes. Now you cannot go against the building code. That's a different situation. It's semantic, yes, but this is law and these are recommendations. That's what I would say about that. And there's the AASHTO also. There are many codes, specifications. Particularly when I refer to specifications and codes, I don't make distinction, except it has the word building before. Then it's a different story. When it's a building code, then it refers to this. But I'm gonna use specification and codes indistinctly within this course. So that's it for today, or for not today, for this lecture. Next lecture, which is the continuation of this, I'm going to be talking about the different type of loads. Keep watching, guys. See you later.